Like you also have a lot of continuous optimizers. And so this is like, it's a talk about a discrete optimization problem, which will be the Nash social welfare and weighted Nash social welfare. But I will actually, it won't be a typical talk I would typically give. I'll only give you a series of mathematical programs. There will not be any algorithms on it, but the claims that these mathematical programs are inherent for some algorithms. Okay, good. I'll talk about a couple of joint works, more recent with Adam Brown, who's at Georgia Tech, Aditi Ladda, who was at Georgia Tech and now moved to Yale, and Madhusudan Pittu and CMU, and some also older work with Nima Nari from Stanford, Shayan Ovish-Garan at UW, and Amin Saberi, also from Stanford. Okay, good. So let me just define you what the problems are. So let me start first by the Nash social welfare. The problem is as follows. I'm given a set of n agents and a set of m goods. Think of the number of goods be more than the number of agents. And for each agent and each good, you have a certain value, non-negative value, how much they value that good. This agent values that good. And our goal is to assign these goods to these agents to maximize a certain objective. And the objective you're going to say is, for each agent, if I give them a bundle, they'll just add up the values. So it's additive valuation for each agent. But then if every agent gets a certain value from their bundle of the items that they receive, question is, how am I going to combine these values? I'm just going to take the geometric mean of them. Okay. So this is called the Nash social welfare objective. It's been classically studied for more in the setting of divisible goods. Okay, we are going to mainly focus on like where we find assignment. But when you're divisible goods, you can actually give a fraction of some this item to this person and another some other fraction to that. More formally, you have to find xij's, which is a fraction of item j that you get to agent I, and then the valuation. And so, of course, if the constraint would be to that every item you can only use total fractions have to add up to 1. And this will be the valuation because it's still additive. If I give you half item, then your value objective is half the total value that you get from the unit item. And then again, you do the geometric mean. This one has been classically studied, goes back to the work of Nash and Nash bargaining. He actually took a very axiomatic approach. He said, I don't care about any objective. Let me ask the following problem. I have some very natural objectives or like axioms that any allocation rule must satisfy these 4 axioms. And what are the possible objectives that I wouldn't want to optimize to satisfy all those axioms? And he proved that the only unique one is this objective. Okay, I won't go into what those axioms are, but the couple of them are very nice properties about this. That's a scale free. Every player can tell their own valuation in their units. Okay, whatever your units could be dollars or whatever. Like, yeah, so it's completely scale free. So just a thought to see. Like, I can tell in my units, you tell in your units. There is no going to be comparison between us, both of them. And the other thing is nicely combines efficiency and fairness. There could be a very nice paper by Kargianis et al., which basically showed that even in the discrete setting, there's unreasonable fairness of Nash social welfare. That's the title of the very nice title of the paper. Of course, building on some older titles. But yes, I won't go into detail, but it is this objective wants you to give items to players who value that item quite a lot, as well as won't force you to basically make somebody not getting any items. So it does combine both of them. Good. So that's the Nash social welfare objective. I'll come to this divisible one bit more. We'll talk a bit more about that as well. So let me tell you the more general problem as well, which is the weighted Nash social welfare problem. Actually, after Nash's work, there was a lot of works which followed by looking at his axioms and asking whether they are the right set of axioms or can you change them. Then one of them was by Kalai, and he dropped what is known as the symmetry axiom. The symmetry axiom was that if you permute the players, you still your allocation rule should not depend on the name of the player in some sense. And if you drop that, then Kalai showed that the only objectives which satisfy the remaining axioms are what are known as weighted natural social welfare objectives, which are defined as follows. Additionally, for each player, I'm going to give you a weight which add up to 1. So the sum of the weights will add up to 1. Non-negative weights, and this time you will take the product of the value of the bundle for player I to the power of wi. So if the weights were all equal, 1 over n, we will exactly get the geometric mean. Otherwise, we're getting some weighted geometric mean of them. Good. So these are the two problems I will solve, and both these problems are NP hard, and actually they're APX hard. So we will basically be looking at approximation algorithms, except I'm not going to give you any algorithms in this talk. What the main of the goal of this talk would be to introduce you some convex and non-convex relaxations for both these problems, and which will have some worst case approximation guarantees. For this, you will have to believe me a bit as well, but at least I'll try to convince you why there exists some worst case approximation guarantees. And something mainly you want to think about it is, if I want to just estimate the value, what you can get, right? I give you an instance of these problems, and you want to estimate me what's the value of the objective, the optimum solution, right? So question is, one way to estimate is to write some relaxation and solve that relaxation, and the value of it will be my estimate. Okay, so we would try to understand how can we write that, write such relaxations. Okay, so the first one, so first half of the talk, I'll mainly focus on the Nash social welfare, and then weighted one problem is clearly more general. So then we will piggyback on the work that had been done for Nash social welfare and come to the weighted one, right? So I'll go back to the standard Nash social welfare where there are no weights. All the weights are 1/n. Good. So how do I write the first relaxation? Well, the first relaxation is I allow you to divide the items. Okay, good. So in the Nash social welfare, you can't divide the items in pairs. You have to give every item to only one player. But if I allow you to divide it, then you exactly get a convex relaxation. But of course, the objective function is not, well, actually it is in that sense. But if you take a log, then you can easily see it is actually convex now. You get this is a concave function. You're maximizing, so you get a tractable relaxation. Okay. So good. So I've just taken the objective and taken a log of it. Okay. So this is my first crack at the problem, and this is the relaxation which was studied by Nash, and actually it shows up in lots of settings basically. Yeah, like if you look at many kind of fairness regimes where, like even for example TCP/IP protocol and so on, these are exactly the kind of objectives actually which show up as well over there. Okay, but for our problem, actually, this is a terrible relaxation. Good. Why is it a terrible one? For example, even if you have a single good but two agents, okay, clearly then the optimum answer is 0. But this, like I've taken a log, but really if I should take exponent again. But if for this convex program, actually we'll split the item into both of them, and both those players will be happy because they at least got something, right? But I know there is no feasible solution over here which will get you a non-zero objective. But the convex program can get you that, okay? And we are aiming for something which are multiplicative approximations, which are not good, okay? So such a setting is really bad. Just to tell you, and I'll come to this, there was a very nice paper by Cole and Katsilis in 2015 who gave the first constant factor approximation for the Nash social welfare, right? The standard problem that we're going to look at. I'll come to that. But before that, I'll give you a slightly different relaxation, okay? A stronger relaxation. So this bound can be significantly higher than what the real answer is, right? Even if the real answer is 0, it can give you a non-zero answer. Question is, how do you get a better bound? So this was work that we did with Anari, Oveshgaran, and Saberi. Good. So this really, it's a nice one. What I've done is, now I'm going to think of my objective as a polynomial, okay? And the way what we're going to do is, this is my convex program. I'm maximizing over all fractional allocations as we were doing before. So this thing has not changed, except my estimate. If you give me a fraction allocation, what is my estimate for that? That's going to change. Earlier, it was just log of summation xij, vij. I summed up of that. Now I'm allowing you to scale the values for the items. Okay, so think of ij's as a certain scaling. Y's are non-negative. We'll think about what those scalings are. So every item, now I will scale it. Okay, its value from Vij to Vij times Yj. That's all what you should think about it. And I'm going to take a minimum over all possible scalings. But of course, what are my feasible scalings? My feasible scalings will be the following, that if I take a product of any n items, their scaling factors should be at least 1.
What is the integer solution here?
X is what you're optimizing over.
For y, it's just 1. So
no, y is your minimum, right? So if y were 1, then you're back to the original program, which we saw before. So that's not a good idea. You should possibly put a different y in that sense, because I'm going to take a min over y. So for a fixed x, I'm going to take my best bound, right, which is a min over y. I'm not.
What is the integer solution?
So there is no integer solution, right? Because it's, think of it that way, for a fixed x. Okay, good. So what we should first see is, why is this even a relaxation? Okay, that this is a relaxation. And those are the kind of the only proofs I will show you that the convex programs I'm going to write. Firstly, I haven't even showed you this is convex. Okay, but I think maybe Melanie's talk might actually already start showing you that it is actually there is some nice convexity overhead. Yes, there?
Misunderstanding something. The y's are on the products or on the players?
On the items.
So I don't understand how they get rid of your previous integrality gap. Because if I only have one, then I'm going to set that y1 to 1, and it's gone.
So good. Because this is saying for any subset of that particular size, then I will put y to be 0 actually, because there's no subset of size 2 over there. So that way I'll take it to 0. Okay, so that's a extreme case, but really my constraint is only for subsets of size 2. So in that case, they don't have any constraint actually for that particular case.
But then how does it get rid of the
So, but because then I will basically set yj to be 0. So I'll just take the scaling factor to 0 over that case. Maybe I should have made a better example, but okay, let's just try to understand, why is this even a relaxation? Okay, good. Why is this a relaxation? So let's say, what do I need to show you about relaxation? If I pick an integral solution, like basically this objective value should be bigger than the value of that integral solution, any integral solution, right? So for any integral solution, sigma, let's say it's assignment, x I will set to be the indicator vector for that assignment, right? Xij to be 1 if sigma is telling you to assign that good to that item, right? Item j to player I. Good. So let's just plug that x, and I'm going to show you that this minimum value will be at least the value of that integer assignment value. Okay, why is that the case? So I'm going to take the min over all y, and I'm going to think of it like, write it this way. I took the sum inside the log. Okay, so because I really want to think of this as a polynomial in y. Okay, the sum, I took a product. So what is this polynomial? These are linear terms. How many of them? There are n of them, one for each player. So this is a degree n polynomial, correct? This is a degree n polynomial in m variables, or number of items. But it's a multilinear polynomial now, right? Because each item will only be assigned to one player. It cannot appear in two different linear terms. Okay, so if I expand it out, I'll only get multilinear terms of what degree? Will degree exactly n, and my constraint says that all of these terms must be at least 1. So I can say that this is at least as if these terms were not there, right? So these y variables really, like, if they were all 1, it's clearly a relaxation, is what we had before. But by putting these constraints on q, it's behaving as if they're all 1. But of course, my constraints are only on their products, right? So this will be exactly as this term will behave exactly as what I want it to be. So it's a relaxation. Okay, good. Yeah. So and I really need to show for every y it works, not for a fixed y, right? Yes. Good. Actually, and this is a very good bound. Like you can look at, because if we are in log space, if I look at the optimum value, it's a relaxation. So the first inequality is that the convex programming value, this value is bigger than the logarithmic of my optimum value, and you can show it's within, because I'm looking at the multiplicative approximation. So in the log scale, it should be additive. So in the additive, I only lose something like a log of e. So it's get you a e approximation. So this proof, okay, we're not going to do, because this really relies on algorithms, but really there are some inequalities on stable polynomials. That's what is needed for proving this result. Okay, questions? Yes.
Sorry, so just to understand, this is an e to the n approximation of the. No. You have a 1 by n in the.
Yes, exactly.
E approximation.
Yes. So actually, I'm not going over there, but actually, this e to the n, you can think of a way, is the same one that comes for Gurwitz bound for permanence. So, and there is a relationship to that as well over here. I'm not like, yeah, okay, but maybe that's a different talk. Okay, good. So let's keep going. Like, yeah. Okay, so there is a different work which I promised you, like Cole and Gutslistics. Really, they didn't really write an explicit convex program, but which was followed up by Cole et al. They wrote a different convex program. Okay, so this is even weirder. Okay, and at least only now I would say at least I have some understanding. Maybe hopefully I'll try to get across. So you looked at the classic one, like the basic one. Let's go back to our basic one, which is bad. We know this is a bad convex program, but actually this one, there is a very nice work which shows that this is equivalent to a convex program given by Smyrev for a different problem for market equilibrium. And I'll explain what that is. But the equivalence really is via some market equilibrium problem. In particular, this program, you can reformulate it as an Eisenberg-Gale market equilibrium problem. and for which this is another convex program which is known. Okay, so what is this doing? Let's just see. So Bij variables are not assignment variables. What are my constraints on Bij? They are saying, think of it this way, every player gets $1 of budget which they can use to buy different items. So that's what this constraint is, right? It's not that every item being assigned. Here, every item is being assigned fractionally. So the sum is over, the constraint is over for the items. Here, my constraint is over every player. Every player gets one. And for every possible assignment, I have a certain objective, which is like a very entropy kind of objective. First term is a linear term, but the second term is a non-linear term, which is a very entropy kind of objective. I won't go into detail where this comes from, but basically this is a convex program that is known. These are equivalent. Well, that doesn't bias anything, but for at least let me try to convince you that it's a relaxation again. Okay, so so for example, what is a feasible B, right? What is a feasible B? The feasible for integral assignment. For integral assignment, the Bij that you set it to be, well, if you don't give item j to player I, then you set it to 0. Otherwise, you give it what fraction of value this player gets from this item. Okay, so Bij divided by Vi, where Vi is the sum of all the values that this get, right? There's a fraction of the value this player gets from this item. So clearly, if I sum for any player, all the values that he gets from all the items that he's assigned, this will sum up to 1. So that's a constraint. And if you plug this assignment in the value, you will exactly get the log of the Nash social welfare objective. Right? That's just a calculation. I won't do it. But you can believe me, that is true. Okay, good. So we have also got one more nice relaxation, but we know these are equivalent. So this one was crappy, so will this be, right, for our discrete problem, right? So that doesn't help us. But now we can strengthen this, okay? And that's what was done by Cole et al. What they said was the constraint they will add is, which is what they call the spended restricted convex program, is that for every good, the sum of the Bij's, which will add up to a good, will be no more than 1. Okay? And this will still remain a relaxation. Why is that the case? Well, in the integral solution, for a good, only one Bij was non-zero. It was for the I for which this item was assigned. And what was that? Well, it was a fraction of value that this item was providing to that player. Clearly, that fraction is no more than 1, and only one of them was non-zero. So this constraint is always satisfied. So clearly, this is a strength, like this is still a valid relaxation, and it's a strengthening. And these people basically showed that actually this is a very good convex program. It gives you a bound within, like it's a relaxation. That's the first inequality, and it gives you a bound within a factor of 2. Okay, at least, yeah, like in the log space, so it's additive 2. I won't prove it. I'll just convince you why intuitively such a proof will be true, is that the support of this is actually a forest. So if I look at only the Bij's, which are non-zero, and look at on the graph, my graph is a bipartite graph, right? Players versus items. That actually is a forest. Okay, let me convince you why that is true. Well, the objective is convex. In terms of some sense, you shouldn't expect sparsity. But then you do the following thing. You say, this is a linear term. For the non-linear term, whatever is inside the log, let me actually fix it, whatever it is. You give me optimal solution B star, let me fix this quantity. Okay, that's one constraint for each player, which is the same quantity as over here. And once you fix that, what you get is just an assignment LP. Okay, and we know any extreme point solution to assignment LP will be a forest. And then you can look at David's book to figure out how to convert this into an integral solution. It's not much different than some of the things that he does for some scheduling problems. Okay, but what you get is basically a factor 2. Okay, so now at least we've done Nash social welfare. I'll move on to the weighted one.
Strictly contained in your relaxation.
Good, we'll come to that as well. Okay, good. Yeah, so yes. So yeah, you're going from a punchline, but we'll come to that later. So good. So we started with these 3 of them, right? The assignment convex program, the Eisenberg-Gale convex program, and the Smirnov, right? I didn't give you the Eisenberg-Gale, but basically more or less. So these were all poor approximations. They gave poor bounds. We strengthened assignment to this polynomial one, and then we strengthened the Smirnov one to the spended restricted one, well, or whatever the Cole et al. Did. And both of these gives you constant factor approximations. Good. So that's how. And now I want to move to the weighted version of the problem. Good. So the weighted one, as we just said this overhead, that's what the main part of this I wanted to go. So just recall, you also have weights which sum up to 1. Okay, good. So what you want to do is, of course, look at these convex programs and generalize them to the weighted version. Okay, so that's what we do. Okay, good. So the first thing you do is we go to the spended restricted one and generalize it. What we do is basically the first naive thing you would want to do is plug in the weight. Wherever you saw 1 over n, replace 1 over n by a wi, okay? And you do that, you get exactly what this is, okay? And it doesn't, like, yeah, so your objective, this had 1 over n in the linear term, and then you had the entropy term where you had a 1 over n, so I just plugged in the wi over there. And it turns out this is actually a relaxation. It requires some care, but it actually is not too much more difficult. And you run the same argument that the support is a forest, you can round it. All of those arguments are a bit more involved, but they work out actually. Your constant factors are a bit worse. It's a relaxation, and it's not much worse, okay? And the support is remains still a tree. The same arguments still work out. The problem now is the following thing. This is not a convex program, okay, which is crazy actually. Like this function is convex only if the wi's are all equal. Okay, for a general wi, this is not convex. It almost like, yeah, okay, I couldn't believe when I worked out the calculation, but that is actually true. So this is not convex. But if I give you, I can actually given a fraction solution, I can actually round it very well. The rounding algorithms I can generalize over there, right? Whatever they were, we didn't go there. So question is, what do we do now? What we did was we wrote a different program, right? So this is the non-convex program. I'm going to write you a different one, and maybe I'll try to give you some, like it'll almost look crazier, but I'll try to get into the mystery a bit more. So I'll change my objective. I'll basically add two KL divergence terms. One is, think of the weight vector as a probability distribution, and I'm going to take its KL divergence with the uniform distribution, right? This is both distributions over pairs. Then I will also take two distributions, given a fixed B, two distributions over the items, okay, which are the following. Okay, I won't go into the detail in the interest of time. And I'll just basically, to my non-convex term, I add this and subtract this. And lo and behold, this function is actually a convex one now. Maybe it might look mysterious to you. This is a convex relaxation, and good. And so now if you stare at it, we are actually have a very, like, at least approximation. Why? Because these two objects, this term is non-negative. Sorry, this KL divergence are non-negative. So this term I can drop. How much worse I'm getting is exactly the KL divergence between my weight vector and the uniform distribution. Okay, so that's what my approximation would be. My approximation would be basically the KL divergence times some constant for factor. Okay. Good. So in the interest of time, let me just quickly say that basically this convex program will give you a polynomial time approximation, which depends on the KL divergence between the weight vector and the uniform distribution. Okay. Maybe I might have gone too fast. Question is, how do I even write this convex program, right? Okay, and that's what I'll just tell you quickly, and then I will end. So the way to do it is as follows. Recall, like, basically what we have done so far is we looked at this spended restricted convex program. For the weighted version, I wrote down a non-spended restricted non-convex program and some of these entropy kind of terms, the KL divergence term added, and I wrote these convex programs over here as well. Okay. So question is, how did we get this convex program? The first thing we noticed, what Santosh was saying, was what are the relationship between those two convex programs for the symmetric version. Actually, they're both equivalent. That's the first thing we showed, was that the polynomial one as well as the spended restricted one, they are actually equivalent for in this case of when you have the standard Nash social welfare problem. And the polynomial one, actually, we can generalize very easily, and it still remains convex. Okay, and then you ask yourself, you get a polynomial optimization problem which is convex, and what is it equivalent to now in the weighted setting? It turns out to be exactly this one. Okay? And here we know in this view, in the spended restricted view, we can convert it into integral solution because of nice properties, but that's basically what is happening. Okay, don't have so much time like now, but basically this was a convex program, polynomial one that I showed you was a relaxation for the Nash social welfare. This is the one for the weighted one. Here you plug in the weights at appropriate places, okay, and stare at it. Actually, I never showed you this was convex. All right, I never showed you this is convex actually, and you should be a bit careful in assuming it's convex, because in X, this function has to be log, like it has to be concave in X because I'm maximizing. In Y, it has to be convex. But actually, in Y, it is not convex. My constraints are not linear in Y. You actually have to go to log of Y entry-wise, and then actually becomes convex. Or you can appeal to Milanese talk, and basically you will get geodesic convexity in Y as well. Right? That's another way to view it as well. Okay, but that's basically to fill the picture. That's where it is. So right, and now you will basically, at least this is a picture I want you to keep in mind. If at all, there are a lot of these convex programs, but some of them nicely generalized to remain convex. The other ones, but sometimes to round it, actually, you need a non-convex formulation, right, to get an integer solution. That's where we really used it. Okay, the bounds we only get right now is only in exponential in the KL divergence. So just to conclude, basically, I just give you results for Nash social welfare and weighted Nash social welfare. I mainly focused on convex and non-convex mathematical programs. There are other approaches as well. Although I want to say they're really inherently using the same convex programs at the back, but basically work by Garg, Husik, Lee, Vague. Sorry, apologies. There's a typo over here. Vague, Bondrak. They wrote a series of papers, and some of these works actually work also in slightly more general settings, actually significantly more general settings of valuation functions, not additive, but some order and so on. The best approximation factor for Nash social welfare in the additive setting is actually due to Berman, Krishnaswamy, and Vesh. They give a combinatorial algorithm, but intuitively, I want to still say like there's some convex programs are still underlying them as well. But the main one question, at least for weighted Nash social welfare, is there a constant factor approximation? We still don't know. The other one actually is something that bothered us quite a lot, and maybe like there are a lot of experts in this room who can tell us more. Actually, what is like solvability of a non-convex formulation? Of course, that's hard. I don't want to solve it exactly. Okay, at least get me a local optima. Okay, I don't care about local optima. Just get me a KKT point. Okay, actually, even just getting a KKT point in polynomial time, it's not clear to me how I would do. And then I I was just talking to some people, and they pointed me to this paper. Actually, computing a KKT point is actually CLS complete as well in general. Of course, the natural question would be like, when can one characterize, give conditions, when can you find a KKT point in polynomial time, under what conditions at least, and which can capture some of these, or other nonlinear, non-convex programs. I just don't know exactly what the algorithm would be for that as well. And polynomial, I really mean polynomial, and as in polynomial in the bit size, right? Bit complexity. Okay, good. That's what I want to say. Thank you.
Thank you. Very interesting talk. I think in the interest of time, we're just going to go to the next talk, and we can have questions offline.